Hello everyone. Today is our first course of our biomedical imaging principle course, and this is our introduction course. In this lesson, I will give you some brief reminders, most of which you already know. We will talk about now some numerical values, and we will use in our following courses some basic constant in SI unit system, like for energy, joule, for temperature, Kelvin, Coulomb, for electric charges, ampere for current, Newton for forces. For the magnetic force, we will use Tesla. And as you see, we have some constant in the slide. And Avogadro constant is the proportionality factor that relates the number of constituent particles. These particles are usually molecules, atoms, or ions in a sample with the amount of substance in that sample. Its SI unit is reciprocal mole, and it is defined as Na. Boltzmann constant Kb or K is the proportionality factor that relates the average relative kinetic energy of particles in a gas with the thermodynamic temperature of the gas. R is also known by alternative names such as ideal gas constant, molar gas constant, or simply R gas constant. And R gas constant is a common for all gases, and the numerical value of this constant depends on the unit used to describe the remaining entities in the ideal gas equation, such as pressure, temperature, volume. We have some charge values, unit charge values here. Let's define the elementary charge. Elementary charge usually denoted by E or sometimes QE is the electric charge carried by a single proton, or equivalently the magnitude of negative electric charge carried by a single electron, which has a charge -1 E. This elementary charge is the fundamental physical constant. To avoid confusion over its sign, E is sometimes called elementary positive charge. And atomic mass unit, the atomic mass is the mass of an atom. In SI unit of mass is kilogram. The atomic mass is often expressed in the non-SI unit, Dalton, where 1 Dalton is defined as 1/12 of mass of a single carbon atom at rest. We have another constant here, permittivity of free space. Epsilon 0, commonly called vacuum permittivity, permittivity of free space, and distributed capacitance of the vacuum. It is the capability of electric field to permeate a vacuum. Another constant, we have Planck's constant. It is the quantum of electromagnetic action that relates a photon's energy to its frequency. Planck's constant multiplied by a photon's frequency is equal to photon's energy, and the Planck's constant is fundamental physical constant denoted as H. Let's look at the other one, magnetic moment of electron. In atomic physics, the electron magnetic moment, or more specifically, the electromagnetic dipole moment, is the magnetic moment of an electron caused by its intrinsic properties of spin and electric charge. In MRI, we will talk about this more detailed. So, you see a list of powers often used throughout science and SI units here. So you can also see the velocity of light, electron charge, electron mass, proton mass values in their SI units. We know Planck's constant. And then let's talk about Bohr radius. It's a physical constant equal to most probable distance between the nucleus and the electron in a hydrogen atom in its ground state. So I will define some common terms. Power is the rate of change of energy with time. It's measured in watts. 1 watt is equal to 1 joule per second. Such as light bulbs are rated by power that they consume 40 watt, 60 watt, 100 watt, etc. So a 100 watt bulb dissipates 100 joules of electrical energy each second. Temperature is the property of systems in contact that determines whether they are in thermal equilibrium. The concept of temperature stems from the idea of measuring relative hotness and coldness, and from the observation that the addition of heat to a body leads to an increase in temperature as long as no melting or boiling occurs. Field, so a field. Electric field, magnetic field. In our following courses, we will use this term again and again. A field of force is a region in which gravitational, magnetic, electrostatic, or other kind of force can be exerted on an object. These regions are imaged to be treated by lines of force, and the lines are close together where the field is strong, and proportionality wider spaced, it is weaker, where it is weaker. The concept of action at a distance or a field of force was first introduced by Newton in his theory, universal gravitation. It has since become a central theme in modern physics. Each of the fundamental forces, for example, gravitation, electromagnetic, or nuclear forces, has a characteristic scale of length. Let's look at the definition of atom and ion. A natural atom has the same number of protons as electrons. A positive ion has an atom with one or more electrons removed, and a negative ion has gained one or more electrons. So as an example, you can see a neutral lithium ion with zero net charge, positive lithium ion with a positive net charge, and a negative lithium ion with a negative net charge. Another electricity definition to remind you, what keeps the constituents together and provides the basis of function in the living cells? The answer can be formulated easily: electrodynamics. Atoms and molecules are built up by forces between negatively charged electrons and positively charged atomic nuclei. The light electrons are not particles in a conventional sense with definite positions and motions, but rather distributed in what somewhat loosely can be considered as electron clouds with well-defined properties. These lie around the nucleus in an atom and stretched around several nuclei in molecules. Such negatively charged electron clouds around more localized positively charged nuclei hold the molecules together and contribute their structures and properties. The basic forces are electric forces between charges. The other is electromagnetic forces, and the other is nuclear forces. The fourth force is nature. The fourth force of nature is gravity. So let's go on with general electrostatic definitions, and let's talk about Coulomb's law. Electricity begins with electrostatic and the electrostatic force, one of four fundamental forces of nature. Electrostatic force described by Coulomb's law. We use Coulomb's law to solve that forces created by configurations of charge. Electrostatics deal with forces between charges. Static means the charges are not moving, or at least are not moving very fast. Having said that, we now turn to electrostatic in concerned charges and forces between charges and the importance importance for our purposes. The main constituents of life, the primary molecules, are built up by charges, electrons, and atomic nuclei. So a starting point is usually concentration of charges surrounded by empty space and mutual forces between them. The basic statement is Coulomb's law, which says that two charges influence each other by a force that is inversely proportional to the square of the distance between the charges, as you see in the formula on the right figure. In this figure, Coulomb's constant is Ke. So the force is also proportional to the product of charges, and its direction depends on the charges. If they have same sign, both negative or both positive, the charges repel each other, and the force on one of charges is directed away from the other one. If the charges are of different types, one negative, one positive, the charges attract each other, and force is directed towards the other one. Magnetism is the force of attraction or repulsion of magnetic material due to arrangement of its atom, particularly its electrons. It is a result of unbalanced spin of electrons in the atom. All magnetic phenomena result from forces between the electric charges in motion, and the magnetic effect is strongest at the end of magnets, and they are called poles. And the magnetism is closely linked with electricity. The magnetic field affects moving charges, and moving charges produce magnetic field. Change in magnetic fields can even create electric fields. The ultimate source of any magnetic field is electric current. Now, after the some electrostatic definitions, magnetism definition, after some brief information about these, now I will give you some brief reminders about the electromagnetic spectrum. Electromagnetic waves are made by vibrating electric charges and can travel through space by transferring energy between vibrating electric and magnetic field. Any moving electric charge is surrounded by electric field and a magnetic field. A change in magnetic field creates a change in electric field, we know that. The distribution of continuum of all radiant energies can be plotted either as a function of wavelength or of frequency in a chart known as the electromagnetic spectrum. in this electromagnetic spectrum, the electromagnetic waves range from the shorter wavelength, including X-rays and gamma rays, to longer wavelengths like microwaves and radio waves. And its frequency, as you see, inversely proportional with the wavelength in the electromagnetic spectrum. We can see it. And we have a visible light region we will talk about in the following slides. So the electromagnetic waves are grouped into the types that have similar wavelength and so have similar properties. You can see their wavelength values and how frequency and energy changes in the figure. Okay, you know all electromagnetic waves travels in speed of light, and all electromagnetic waves are transverse wave. We can define direction of energy travel, direction of medium oscillation, amplitude. You can see amplitude of it, and then one complete wavelength, lambda. You can see these in the figure. These are basic things about the waves, and then not only for electromagnetic waves, also these amplitude and wavelength definition valid for sound waves. For example, in our ultrasound imaging technique, I will also remind you the wavelength amplitude details. So properties of electromagnetic waves. They do not require any medium to travel through. They can travel in space. And then they travel at speed of light, which is 3 times 10 to the power of 8. So this is the speed of it in vacuum. Electromagnetic waves can be reflected, can be refracted. They can be absorbed. And they can transmit from the media, from the tissues. They can scatter. So it is possible for the electromagnetic wave and tissue interactions or matter interactions. All of these are possible. Yes, they all obey the wave equation. Here, the lambda is wavelength, length of one complete wave. You know, frequency of the wave hertz, and it's actually number of waves that pass a point during a certain time period. And then amplitude, distance from the origin to the trough. And the formula is speed of electromagnetic wave is equal to frequency times wavelength. Their frequencies do not change as they pass from one medium to another. However, both their speed and wavelength will change. They carry energy from one place to another. They are all natural charge, as all of them oscillate with electric and magnetic field perpendicular to each other. As you see in this figure, you can think the red areas as magnetic field and the blue areas as electric field. They propagate together. Yes, radio waves. They have longest wavelength and lowest frequencies of all electromagnetic waves. Radio waves are the electromagnetic waves. They can travel through a vacuum. However, most of the radio waves we receive have traveled through air. Take the radio as an example. The radio converts the electromagnetic waves into sound that comes out of radio speakers. We will talk about radio waves in magnetic resonance imaging. But we know that they can be used in radar and satellite navigation or ships and aircrafts. These are daily usage of the radio waves. Microwaves are the radio waves with wavelength less than 30 centimeter and higher frequency and shorter wavelength. Cell phones and satellites use microwaves between 1 centimeter and 20 centimeter for communication. One of their most common use in which microwave ovens, when you switch on a microwave oven, it gives off electromagnetic waves that bounce around inside the oven, penetrate in the food, and the water molecules in the food absorb energy from the microwaves, causing the food to get hot. Infrared. Heat can be transferred through infrared radiation. We often think infrared is being the same thing as heat because it makes our skin feel warm. Most of you might have seen infrared waves in the use during COVID pandemic, for example. If you look at the picture on the top right-hand corner, it shows a thermodetector which is placed outside hospitals, airport, to identify the warm and cool parts of a person by analyzing infrared radiation emitted from a person's body. And on this, we can see if someone is having a fever. Infrared useful for navigation through fog and haze as it is less easily scared compared to visible light. Also, it has some medical treatment areas to warm injured muscles, sports injuries. Yes, the upper figure actually shows us the thermogram. So a picture that shows regions, different temperatures in the body. Temperatures are calculated by amount of infrared radiation given off. Therefore, people give off infrared rays. So visible light, the light which our eyes, our sensors can detect is part of the visible spectrum. Some remote sensing instrument also detects radiations invisible to our eyes. Range of visible wavelength is from 400 nanometer to 700 nanometer. And then longest visible wavelength is red and shortest is violet. And the white light contains a mix of all wavelengths in the visible region. Okay, an example of visible light can be also the colorful laser light or the light from a firework. Some of the uses of light is in the optical fibers in medicine and telecommunications. Gamma rays have the shortest wavelength and the highest frequency in electromagnetic spectrum. It is generated by changes in energy levels in the nucleus. Some radioactive substances and certain nuclear reactions produce gamma rays. Because of their high penetrating ability, gamma rays can use serious illnesses. Also, we can use in some medical imaging methods we will talk about in our following courses. Gamma rays are used in nuclear medicine imaging techniques such as gamma camera scans and positron emission tomography. These techniques involve injecting or injection radio tracers that emit gamma rays, and gamma rays emitted by the tracer are detected by specialized cameras to create images of internal organs and tissues. So this allowed the physicians to diagnose diseases to evaluate the organ function. Radiation therapy, we can use gamma rays for sterilization. These are medical application areas of gamma rays. Yes, X-ray. So shorter wavelength and higher frequency than UV rays carry a great amount of energy. We produce X-ray by using a specific tube, X-ray tube. They can penetrate most matter. For example, bones and teeth absorb X-ray, but we have to use this in some limits. Too much exposure can cause cancer. It can be also used by engineers to check tiny cracks in the structure. For example, the rays pass through the cracks and cracks appear dark on the film. As you know, it is used in Röntgen and computed tomography procedure, which we will talk about in our following courses. We will talk about again the X-ray penetration ability and which tissues absorb more the X-ray. Ultraviolet. The main source of ultraviolet radiation is sunlight, and it is this radiation which gives rise to suntan and also sunburn. Ultraviolet radiation used in hospitals to sterilize the surgical instrument and operate in theaters as it kills bacteria, viruses. Yes, sunlight contains a range of ultraviolet wavelength divided into three main categories: UVA, UVB, UVC. UVA wavelength is between 320 and 400 nanometer. UVA is the most abundant UV radiation reaching the Earth's surface. It is responsible for tanning and contributes to the aging of the skin. While it is not as strongly as absorbed by ozone layer, excessive exposure UVA can still have some harmful effect on skin. UVB radiation wavelength is between 280 nanometer and 320 nanometer. It is partially absorbed by the Earth's ozone layer, and it is primary cause of sunburn, and it is also associated with an increased risk of skin cancer. UVB plays a role in synthesis of vitamin D in the skin. And UVC is the shortest wavelength and largely absorbed by Earth's atmosphere, particularly the ozone layer. It is a significant component of natural sunlight at ground level. UVC highly germicidal and used various applications for disinfection. For disinfection purposes, particularly in healthcare setting, UVC light with wavelength 154 nanometer is often used. The wavelength is effective in inactivating microorganisms. Surgery rooms also sterilized by using this UVC radiation. Yes, let's look at some common terms for the medical imaging techniques. Angiogram. an image in which blood vessels are selectively enhanced either by the use of a contrast agent or a flow-sensitive pulse sequence. You can see some examples of the angiogram on the right figure in our following courses. We will look at more detail to this. Image artifact, which image artifacts can be in which imaging, medical imaging techniques. In our following courses, we will also look at this. So image artifact is a feature in any medical image not related to any anatomical structure or physiological process, but produced by measuring process itself. So we have a figure here, MRI artifact example. There is an license of wrap around. So out of field of view anatomy. So we have field of view, but we have out of field of view anatomy, as you see in the right figure. This is an MRI artifact example. We will look at the other kinds of artifacts in the other imaging techniques. So biopsy. Biopsy is a medical procedure in which a sample of tissue or cells is removed from a person's body for examination under microscope. It is commonly performed to diagnose or rule out conditions such as cancer, infection, or inflammation. Biopsies can be conducted using various methods depending on the location of tissue being sampled, including needle biopsy, surgical biopsy, endoscopic biopsy. The examination of biopsy sample by the pathologist help in making a diagnosis and determining the appropriate course of treatment. We have here an example bone marrow biopsy, which is commonly used to diagnose a variety of blood problems, both non-cancers or cancers, including maybe blood cancers, leukemia, lymphoma, multiple myeloma. A bone marrow biopsy may also detect cancers that started elsewhere and traveled to the bone marrow. During a bone marrow biopsy, the doctor draws a sample of bone marrow out of back your hip bone using a long needle, actually. In some cases, your doctor may biopsy marrow from other bones in your body. You receive a local anesthetic before a bone marrow biopsy in order to minimize discomfort during the procedure. In the endoscopy course, we will look at a little more about these biopsy details. Yes, contrast, image contrast. So difference in a local image intensity that differentiates one structure or tissue type from another. And contrast enhancement. So a deliberate increase in the image intensity depicting one particular type of structure. Generally, contrast enhancement is brought about by a change in the measurement procedure. For example, by introducing a strong X-ray absorption substance into the bloodstream prior to exposure. Some contrast enhancement can, however, be achieved by computer image processing, as you see in the upper figure. Maybe age detection can be another example of this. Also, we have an example for the contrast agents. As you see in the bottom figure, gadolinium-based contrast agents help doctors to see abnormal tissues in the magnetic resonance imaging scans with more detailed. And as you see on the right figure, it is more detailed when we use these contrast agents. They help doctors diagnose inflammation, tumor, and blood clots by providing them with clearer, brighter images from inside the body. Yes, field of view. In our previous slides, I told you that. So for the MRI artifact, I told you this term, field of view. So here you see how the field of view is inversely related to the spacing, delta key of samples in key space. Okay, key space. In our following courses, we will define also the key space. For simplicity of explanation, we consider square pixels with the same field of view in each direction. However, by altering the sampling rates along the frequency and phase axis, it is possible to alter the field of view along each image dimension independently. So field of view, the region of body selected for imaging, the X-ray radiography is selected by collimation of incident X-ray beam. The MRI field of view is selected by combination of extent of radio frequency excitation and the range of frequencies accepted by the receiver. A fluoroscopy procedure is also helpful is helpful for treating compression fractures in spine and maybe guiding injections into joints or the spine. A fluoroscopic injection used to identify the source of the pain or ensure that pain is bearable. It is an excellent source of pain management treatment. The fluoroscopic indications are useful in various orthopedic procedures, gastrointestinal investigations, cardiovascular, interventional radiology procedures. It may assist in insertion of implants in cases of fractured bones and position the alignment. Fluoroscopy helped to monitor progress in matters of catheter insertion. So it's a widely used medical term describing the use of an X-ray image intensifier, also sometimes called fluoroscope, and to produce quasi-continuous imaging of surgical and diagnostic procedures, greatly reduced rates of X-ray exposure. Shortly, its definition is like that. Yes, grayscale. In most of our medical imaging procedures, we will talk about this. So in computed tomography, for example, so in our next course, we will talk about this. So grayscale, a digital visual code relating the range of image intensities or colors to a definite numerical scale of values. In general, the scale is chosen to produce the best contrast for anatomical features of interest. In principle, the grayscale is used in X-ray computed tomography, can be absolute so that a particular tissue type has a definite value in Hounsfield units. Yes, mammography, a specific combination of imaging procedures designed specifically allow diagnosis of disease of the female breast, and most commonly the term refers to a specialized X-ray technique made particularly sensitive to a small calcium deposits. Yes, magnetic resonance angiogram, MRA. So a 3D image of blood vessels obtained just the flow of sensitivity of magnetic resonance signal. In magnetic resonance imaging, I will remind you this again. Yes, scanner. So a term often used to describe a particular tomographic instrument. So MR scanner, CT scanner, PET scanner. You can see the example of computed tomography scanner on the figure. Another thing, signal to noise ratio. All measurement processes and instruments introduce some extra random contributions to the signal that they produce. In many circumstances, an instrument might record unintended random and interference signal in addition to the intended signal. The signal-to-noise ratio is simply the ratio of wanted to total unwanted signal amplitude at the output of the instrument. So we have a slice image taken from the brain with high signal-to-noise ratio, good signal-to-noise ratio, which has good spatial resolution, and high low signal-to-noise ratio with high spatial resolution. This is an example how it affects our image. Slice. Yes, you know what is slice, but in our applications, in most applications of tomography, imaging data is acquired in thin two-dimensional blocks or slices. The thickness of the slice is generally chosen between 1 millimeter and 8 millimeter as compromise between the needs of spatial resolution and the signal intensity each voxel. Yes, some other terms. Sonography, it is a widely used medical term referring to all medical ultrasound techniques. And tomography is image reconstruction using large number of different waves of the same object. Invariably these days, the term refers to image reconstruction using digital computer. The first X-ray tomographic imagers were called computer-aided tomography scanners in order to distinguish the technology from earlier classical X-ray methods that highlight a particular plane in the body. Today, computer-aided tomography scanner is referred to simply as CT scanner or computed tomography scanner. Other modalities such as magnetic resonance imaging, positron emission tomography use standard tomographic methods. Yes, these are my sources. Thank you. Next week, we will go on with our first course. We will talk about X-ray, Röntgen, computed tomography. See you.